Hey there, and welcome. When you look at a mountain, or even just the ground under your feet, it seems pretty solid, right? Permanent. But what if I told you that our world is constantly being taken apart and put back together by, well, an invisible sculpture? Today, we're going to dive into the incredible chemistry that's silently shaping everything around us.
So let's start with a bit of a mystery. Just think about those gigantic, incredible caves you see in documentaries. I mean, these things are huge, but they used to be solid rock. So how in the world does all that rock just disappear? How does it get hollowed out to create these amazing underground cathedrals? It really does feel like it's got to be magic.
But of course, it's not magic. The real culprit? It's chemistry. Just a slow, steady, relentless series of chemical reactions that, if you give them enough time, we're talking millions of years, can literally dissolve a mountain from the inside out. And that's exactly what we're going to unpack today. All right, so let's set the stage. We're going to start with what I like to call the rock-eating power of water. See, before any of this cool chemistry can even begin, the chemicals have to get inside the rock. And water is the delivery vehicle. But it can't just soak through a solid chunk of stone, right? It's got to have some kind of pathway in. And those pathways are fractures. Cracks. Geologists call them joints. They're basically superhighways that let water sneak deep down into the rock's interior. And here's the really important part. The more a rock is cracked up and broken, the more open it is to a chemical attack. It's that simple.
Okay, to really get why this matters, let's picture a simple cube of rock. Let's say it's 2 centimeters on each side. If you do the math, its total surface area is 24 square centimeters. That's all the space on the outside that water and air can actually touch and start to work on. But now watch what happens. If we take that exact same cube and break it up into 8 smaller cubes, the amount of rock hasn't changed, but the surface area, it just doubled to 48 square centimeters. So just by cracking it open, we've created all this new real estate for chemistry to do its thing. The bottom line is, more surface area means the weathering happens way, way faster. Okay, so the water has found its way into all those cracks. What happens next? Well, this is where the real action begins. Water has this chemical toolkit, basically 3 main ways it can break down minerals. Let's meet these agents of change. First up, we have something called dissolution. This one's super straightforward. Think about stirring sugar or salt into a glass of water. The solid stuff just disappears, right? It dissolves. It's the exact same idea, but with rocks. Some minerals will just dissolve when they come into contact with water. And hey, check it out. This is the actual chemistry that solves our cave mystery. On the left, you've got solid calcite. That's the stuff limestone is made of. It reacts with carbonic acid, which sounds fancy, but it's really just rainwater that's picked up a little carbon dioxide from the air. And boom, the reaction just rips that solid calcite apart into tiny ions that get washed away in the water. The rock is literally dissolving, one molecule at a time. All right, tool number 2 is oxidation. And you've definitely seen this before, even if you didn't know the name. Ever seen a rusty bike chain or an old nail? That's oxidation. And believe it or not, rocks can rust too. When minerals that have iron in them get exposed to oxygen, they start to change, both in their structure and their color.
So here's a perfect example. We're looking at pyroxene, which is this dark, iron-heavy mineral. When it gets hit with oxygen, it turns into hematite, which is basically just a type of iron oxide or rust, and silica. So next time you're out and you see those beautiful reddish-orange stains on rocks, that's what you're seeing. That's oxidation, and it's a dead giveaway that the rock is chemically falling apart. And that brings us to our third and final tool, hydrolysis. Now this one's a little different. It's not just about dissolving something or making it rusty. Hydrolysis is a total transformation. It's a reaction with water that takes one mineral and completely changes it into a brand new substance. Here's a fantastic example, feldspar. It's super common, and it's a really hard mineral you find in stuff like granite. But when it sits in water for a very, very long time, hydrolysis kicks in, and it turns into kaolinite. And kaolinite is clay. Soft, mushy, weak clay. So think about that. This process takes tough, solid rock and turns it into something soft that can be washed away easily. Okay, so we've been looking at all this chemistry happening at a tiny, microscopic level. But now it's time to zoom out. Let's see how these little, invisible reactions add up to create the huge, stunning landscapes that we can actually see. Ever wonder why some mountains stand tall and proud while the land right next to them gets carved into a low valley? It all comes down to the chemistry of the rocks themselves. It's like a bottle of minerals. You've got calcite, the stuff in limestone, which has pretty weak chemical bonds. It dissolves easily. But then you have quartz, which has these incredibly strong bonds. It's super tough and resistant. That's why limestone terrain gets all carved up with caves and sinkholes, while a mountain made of quartzite can just hang around for ages. And this brings us full circle, right back to those caves. So let's recap the whole process. First, rainwater becomes slightly acidic from the air. Then, that acidic water drips down into the cracks in limestone. Over thousands and thousands of years, it just keeps dissolving the calcite, making those cracks wider and wider until they become huge rooms and passages. Then, if the water level drops, poof, you've got a dry cave. And all those cool stalactites and stalagmites? That's just calcite being redeposited by dripping water. It's dissolution just playing out on a massive scale. Now, as cool as caves are, this chemical breakdown of rock does a lot more. It has a huge planet-wide impact. I mean, it's actually responsible for the way our oceans are. Seriously, have you ever stopped to think about why the ocean is salty? Well, this is it. This is the reason. All those chemical reactions we talked about, they break down minerals and release ions. And those ions are basically salts. Rivers then act like this giant conveyor belt, collecting all those salts from the land and dumping them into the ocean. Then, when water evaporates from the sea to make clouds, it leaves the salt behind. Over billions of years, that salt has just gotten more and more concentrated. The salt in the ocean is literally the ghost of dissolved mountains. How cool is that?
And the wild thing is, all of this is happening right now, all over the world. But it's happening so incredibly slowly on a timescale that's just hard for our brains to even process. Which brings us to probably the most important factor in this whole story: time. Geologic time. I mean, one drop of rain isn't going to do anything to a rock, but trillions upon trillions of drops over millions of years, that can carve the Grand Canyon. It just goes to show you that with enough time, these quiet, tiny chemical reactions are one of the most powerful forces on Earth. It really changes how you look at a landscape, doesn't it? When you realize it's not some static, finished painting, but a living, breathing system that's always in a state of slow-motion change. So I'll leave you with this to think about. What new wonders are being sculpted right now, molecule by molecule, that no one will get to see for another million years?